Welcome to this series of lectures on inorganic chemistry. We're covering topic 9.1, which is the periodicity in period 3. So earlier four lectures focused on the trends in the different physical properties in period 3. We spoke about the trend in atomic radius, ionic radius, melting point. Now we're going to talk about the reactions of period 3 elements. And we start first with the reaction of period 3 elements. Period 3 elements with oxygen. Reaction of the period 3 elements with oxygen. And these are pretty much reactions that you can write straight up, okay, with your background of writing equations, so it should not be a problem. So we'll talk about sodium first. Sodium, when you heat it in oxygen, okay, in a stream of oxygen, it starts burning to produce sodium oxide, okay. The thing to remember is that now when sodium burns in oxygen, it burns with a yellow or orange flame. Okay. It burns with a yellow-orange flame. The sodium oxide produced is a white solid. Okay, so you will be tested on the observation. So that is what you need to remember. Actually speaking, when you heat sodium and oxygen, you will also get a little bit of sodium peroxide, Na2O2 also formed. But your syllabus kind of limits us to sodium oxide. Okay. The second one is magnesium. Magnesium also, you take magnesium ribbon, a cleaned magnesium ribbon. You heat it in the presence of oxygen. Okay. So you are going to get magnesium oxide. This one burns with a bright white flame. Okay. A bright white flame. And it produces a white solid. Okay, produces a white solid. So there's nothing in there. The third one is the reaction with aluminium. Now, aluminium is a slightly tricky case. Okay, we can very simply write that aluminium reacts with oxygen to produce aluminium oxide. But the problem is if you if you look at the reactivity of aluminium, it's actually pretty high in the reactivity series, right? However, aluminium that we get actually acts very stable. And the reason is the aluminium forms a surface layer of aluminium oxide, and this protective surface layer doesn't allow the aluminium underneath the surface to further react. So the aluminium oxide on the surface actually inhibits reaction. This is something that is covered under the properties of metals in IGCSE, so please do look it up, okay? So if you want to have the aluminium reacting, then you need to have freshly powdered aluminium, okay? When sprinkled, all right, in a Bunsen flame and heated in the presence of oxygen, then what happens is it produces white sparkles. It burns, producing white sparkles. And the aluminium oxide is also a white solid. The aluminium oxide is also a white solid. So let's balance this. That should be 3. So it's 6. So multiply that by 2 and that by 4. Okay, now we're done. All right. The fourth one is silicon. Silicon plus oxygen, when heated, it would react to produce silicon dioxide. Okay, silicon dioxide. Now, depending on the type of silicon, there's quite a few allotropes of silicon, though. Okay, of that. So depending on the type of silicon, you could, okay, you'd be required to heat it to say 1000 degrees Celsius. Another form of silicon could react at say 300 degrees Celsius. There is one amorphous white solid, okay, white powdery form of silicon, which actually burns spontaneously, okay, at room temperature when exposed to air. So the data on silicon is actually very, very varied, but you just, as far as your syllabus is concerned, it burns, okay, or it reacts when heated. It reacts when heated. Silicon dioxide is also a white solid. Okay. Silicon dioxide is a white solid, so it doesn't, I mean, as far as your syllabus is concerned, it doesn't react at room temperature, so we'll stick to that. Then we got phosphorus. Okay, phosphorus, again, a bit of an issue because your syllabus kind of limits us to one of the oxides of phosphorus. Well, actually, there are two very common oxides of phosphorus. Okay, there is phosphorus 3 oxide, which has got the formula P4O6. Okay, P4O6. Then there is another form, oxide of phosphorus, which is called the phosphorus 5 oxide or phosphorus pentoxide, which has got the formula P4O10. Okay, P4O10. So phosphorus 3 oxide is a liquid at room temperature. Phosphorus 5 oxide is a solid at room temperature. But when you actually heat it, it burns, producing white light. It produces a white flame on heating. All right. And the two oxides that you get are actually going to come out as gases. So once it cools down to room temperature, you'll find that you have a liquid and a solid produced. However, your syllabus kind of limits us to discussing only this oxide, even though the other one is also there and it's pretty common. Okay. The next one is the reaction of sulfur. Sulfur, when heated in oxygen, produces sulfur dioxide. Okay, produces sulfur dioxide. It burns with a blue flame. It burns with a blue flame. Sorry, I said sulfur dioxide. Yeah, sulfur dioxide. The sulfur dioxide produced is a colorless gas. Okay. Now you're wondering, how do I know that there's a colorless gas produced? It's colorless after all, so I don't see. Yeah, you might not see the sulfur dioxide, but you're very clearly, I mean, absolutely, you're going to smell it. It's got a very, very choking, pungent, acidic odor, so you would know. Okay. Now, you know that there is the other oxide of sulfur as well, sulfur trioxide. However, sulfur trioxide cannot be made directly by reacting sulfur with oxygen. It's not possible. Okay. In fact, in your IGCSE chemistry, you study about the contact process in which sulfur trioxide is only made by combining sulfur dioxide further with oxygen to produce, okay, sulfur trioxide. The reaction doesn't happen normally. It would require a vanadium 5 oxide catalyst, heating to about 450 degrees Celsius at a pressure of about 10 atmospheres, if you want to do it in the laboratory. In the atmosphere, this reaction is catalyzed by the oxides of nitrogen, nitric oxide and nitrogen dioxide, which you'll see later when we do the lesson on nitrogen and sulfur. Okay, so the formation, even though the sulfur trioxide is a stable oxide of sulfur, it is not formed by the direct reaction of sulfur with oxygen. So we do not do that here. Same thing happens with chlorine as well. Chlorine has got quite a few oxides. There's Cl2O, there's Cl2O7, etc. However, none of the oxides of chlorine are formed as a result of chlorine reacting directly with oxygen. Okay, they are usually formed when the different compounds of chlorine, okay, like the chlorates, when they break down, when they thermally decompose, etc. So no direct reaction between chlorine and oxygen to produce any oxide. Same thing goes with the with argon. Okay, so we don't have a reaction. All right. So these are the equations and the observations. However, You will also be asked about the acid-base nature and the nature of bonding in all these compounds, which I've managed to put in a nice little table. All right, which I've managed to put in a nice little table. So if you look at this, okay, now these are the different oxides that are present. There's sodium oxide, magnesium oxide, aluminum oxide, silicon dioxide, okay, also called the silica. There is P4O6, which is not included directly in your syllabus. There's also SO3, which is not directly included in your syllabus in this list, okay? If you look at the bonding, you start as ionic, all right? And then silicon dioxide, it turns covalent. So from there on, it just goes covalent. So you can actually see that as you go from the left to the right, from the metals through the nonmetals, the bonding becomes less ionic. For example, if you think, okay, if you consider sodium oxide to be 100% ionic, magnesium oxide is ionic, but it's not 100%. You can say that, say about 95% ionic, 5% covalent. With aluminum oxide, it goes to about 70-30, so on and so forth. Okay, we'll not go into the details of it, but the trend is as you go from the left to the right, the oxides become less ionic and more covalent. Okay, and that is reflected in the fact that sodium oxide is very highly basic. Okay, it's a strong base. Well, magnesium oxide is a weak base. Aluminum oxide is amphoteric. It can act either as an acid or as a base. Silicon dioxide is acidic. Okay, silicon dioxide is acidic but does not produce acidic solutions, while P4O6, P4O10, sulfur dioxide, sulfur trioxide, they will produce acids that are, okay, progressively more acidic as we go from the left to the right. And this is also reflected in the type of structures that they exhibit. The ionic oxides are all giant ionic lattices. Silicon dioxide is macromolecular covalent. If you remember your IG days, you'll remember that silicon dioxide actually has got bonding and structure similar to that of diamond, while the oxides of phosphorus and sulfur are all simple covalent molecules, and they end up becoming pretty strong acidic solutions when reacted with. Okay, now that summarizes the reactions of the period 3 elements with oxygen. Now, if you're asking what can you be asked? Pretty much everything. It's pretty much recall the whole stuff. You could be asked to complete equations. You could be asked for observations. You could be asked for the nature of the oxide, the bonding of the oxide. Okay, acidic, basic nature of the oxide, whether it's ionic, covalent, etc. So that's the reason why we've kind of summarized everything and put in this table. Okay, so that completes this lecture. The reaction of oxides of the reaction of the elements of period 3 with oxygen. Okay, so I'll see you in the next session where we'll discuss about the reaction of the oxides with water. Okay, so until then, I'll see you guys now. Bye-bye.